Chapter 4, Section 18, Other Physical Control Methods, Radiation and Filtration. UV radiation is a great way to decontaminate surfaces. Not quite disinfection, but definitely a decontamination. Because UV radiation has issues with penetrating through surfaces, penetrating through liquids. But things on the surface, yeah, that UV irradiation is going to go through and it's going to start forming thymidine dimers all through the genomes, whether it's, the prokaryote or eukaryotic genomes, for fungi and things growing on the surface of something. You cause too many of this thymidine dimer formation. Well, turns out that the repair enzymes can't keep up. Repair enzymes are just basically going to get to a point where it's going to tell the cell, the signals are going to tell the cell time to die. Or it's going to do so many mutations that within a generation or two, all the cells are basically going to die anyways. That's why you'll see here's a safety cabinet where you can do, different, genetic, different microbial work. This perforated you see on the back here is blowing air, and there's an air current that keeps stuff from outside getting in. So it's blowing air out. The UV lights you see there are bombarding everything in here and decontaminating the surfaces. Decontaminating, not sterilizing. You want to sterilize, you need to go with ionizing radiation. Okay? This electromagnetic radiation can penetrate. Okay? It can get deep in. You'll see this ionizing radiation in some European countries is being used to sterilize certain meat products, vegetables and whatnot, to kill, like, salmonella on the surface of chicken. So that way, it will have a longer shelf life and reduce the chances of spoiling, reduce the chances of making somebody sick. We also use radiations on non-food things, plasticware, certain surgical supplies you buy from a manufacturer. They'll just put them in the surgical bags, the medical bags, the plastic ones, put them all on a cart, put them into the giant, microwave for lack of a better word. I forget what they're called. And then they all ionize the entire thing. Because ionizing radiation can get through the plastic. It can go through most things that are non-metallic. It hits the metals, basically sterilizes the surface. What's interesting is when you go and you look at who can handle radiation and who can't. You look down here in the footnote. A lethal dose for humans is 10 grays. Okay, 10 grays. 1 gray is 100 rads, so 10 grays is about 1,000 rads. Okay. Our friend Salmonella, 200. Holy shit, that's 20 times what we can handle. Salmonella can handle up to that. Clostridium botulinum, which causes botulism. It's an endospore. 3,300 grays. 3,300. That's what? 330,000 rads in a dose. Holy smokes. So yeah, that's why those endospores are hard to get rid of. Foot and mouth disease, the virus that causes foot and mouth disease. I can't see it behind my head, so you have to go look at table 4.8 in the textbook. 13,000 grays. 1.3 million rads per dose. Holy smokes. So we can go through and we can measure what's the survivability per radiation dose. How many grays in the dose? The D10, 10% survival. They'll do it, what's the LD50? I want to get rid of 50%. You know. We also go and, hey, guess what? We have liquids. Liquids we do not want to irradiate. Liquids we do not want to heat up because they're heat labile. Okay, we're going to use filtration. Filtration is based on either paper, nitrocellulose, or plastic membranes that have small holes or pores of a set size at their minimum. Cool. The minimum size for a filter that says 0.45 micron means that the smallest size there is 0.45 micron. So anything bigger than 0.45 micron will get caught in the membrane. Ones that say they're 0.2 microns. Anything bigger than that hole that's 0.2 microns in size will get caught up. All bacteria, all archaea, all protists, endospores will get caught up. We can do this with liquid. We can do this with gas. Liquid and gas are just going to need different compositions of the membranes. So when you see things like HEPA filters are any filter that has a pore size of 0.3 microns. HEPA means high efficiency particulate air filter. So 0.3 microns. This is going to catch pretty much all bacterial, all fungal cells, most fungal spores, most bacterial spores, and everything bigger than them will be caught by these. Now, the pores can be due to the meshwork of the nitrocellulose. They're saying it's 0.45 because the gap between the strands. Or it can be one sheet that has perforations in it. You know, small ones, big ones. Oh, sorry, on the last slide where I said that the 0.2 microns means that that's the smallest. No, that's the largest pore size, is 0.2 microns. So anything 0.2 microns and larger will be caught. So this could be 0.2 microns, and that itty bitty one right there could be like 0.05. You know, nothing's going to get through the 0.05, but you know, anything that's 0.18 could fit through this 0.2. So this can only get 0.2 and bigger, as they're showing here. The bacteria, the fungi, and whatnot will be caught on the surface of as everything else goes through the holes. We most commonly use membrane filters for liquid sterilization because, well, anytime you go and you mix up something and you put it in an autoclave, you run the risk of boiling off water, which means your molarity concentrations that you calculated and you made will be thrown off, or could be thrown off. You never know. Some of the stuff you may have put in there may be heat labile, so not everything in that broth can handle the high heat. So you go with filter sterilization. If it's a small volume, anything less 10 mLs or less, 20 mLs or less, you can use a syringe, and there are filter adapters that go on the end of the syringe. You draw up what you want to filter into the syringe, you screw on the adapter, and you just push down the plunger. Out comes filtered liquid. If you have a large volume, you can use certain pumps and stuff to go through filters, and then it'll just pull up from here, what you've mixed here. It's being mixed, and since this is open, this is, contaminated. Whatever you put in there, the different components, if they came off the shelf, or in bottles, they're contaminated. This is a pump, peristalsis pump, that's going to be pulling the stuff up and around in the hose and then pushing it through a filter that's attached to this sterile bottle. The bottle, since it was glassware, went through an autoclave, so it's sterile inside and out, or sorry, inside. Outside's exposed to whatever. So as the liquid goes through the filter here, down into the bottle, all vegetative cells, all spores and everything get caught in the membrane. Only sterile liquid goes through.